Compare
Yeah.
the two scales.
Yeah.
Definition, you can get to get the function that is well defined here.
All right, good morning, everybody. So
But I think it's
today, good morning, we have the third lecture by George.
Hey, thank you, Alexei. Oh, good morning. Here in the remaining time that I have, I'd like to bring us into a little bit more detail, but not too much detail, about the broad approach of using perturbative QCD to describe these systems that we can study at colliders. And what we've seen in, I have to get used to this every time. At the end of the last lecture is that we were able to use the concepts of parton distributions and then fragmentation functions, which I haven't gone into detail about, to describe a wide variety of cross sections in at colliders, single particle inclusive and jet cross sections in particular. And what's typical, I mean, of these kinds of plots is partly it's not the agreement with the data in the height. You see, it goes over many, many orders here in terms of the cross sections, but rather the ability of theory to describe the changes with the momentum scale. So if you look for jets at 100 GeV, and then you look at 500 GeV, the number of jets will go way, way down if you're at the fixed center of mass energy, and yet you're able to follow that decrease in the over in the data as you change the scale of the observation. And notice that these are not different experiments. These are just different ways of looking at the same experiment. An individual experiment could or an individual event rather, could be contributing to these curves at two different points if there are two different jets of the same of different energies. So it's really how we select the data that determines the calculations we can make. And when we talk about parton distributions, what the parton distributions will do is to help us also actually set the vertical scale of these curves. But what perturbation theory can do is tell us how these curves decrease. Of course, the parton distributions also be involved in that as well. But that's similar in some ways in terms of how we face data in the world with the calculations we can do. Our ability to calculate these changes is similar to that ability to, in this idealized experiment of sending a gluon and getting a quark into a sphere and having a quark and gluon come out, it's how we can calculate what would happen if we changed the radius of the sphere. It's changes typically that we can calculate in quantum field theory. And this is one of the, one of the great examples. So today, I'd like to do a little bit more, try to do a little bit more formalism about, what are we actually doing? So and the next few slides are tying together almost every use of perturbative QCD. They're all in this form of general form in terms of collinear factorization, but this general form extends beyond collinear factorization. So we're imagining we have some physical cross-section, right, that we go out and we measure. So we make up our minds what events we're going to count, and we prepare an initial state, and then we see how many of the events, come out as a function of time. And so from that, we can derive a cross-section for a particular final state, which we'll just represent by this big Q. In deep inelastic scattering, Q is the momentum transfer that goes that the electron shares with the proton. In a factorized cross-section, these take the form of a short distance cross section, that's omega sub SD, something we can calculate in perturbation theory. Sure.
Sorry about this.
Did it just make up its mind to do that?
Yes, it's happening usually every. should we
Oh,
begin?
an AI companion. So I think I'll be leaving the rest of this lecture.
I think we're still in the meeting, okay, so it should be good. We're still in the meeting, it shows.
Yeah. Oh. Sure.
This computer has its mysterious ways.
Yeah.
It's not possible to comprehend. those
Okay,
ways.
brilliant. Great. Okay, good. So we have the physical cross-section then is written as a convolution. Now here, this is typically an integral over momentum fraction. Or in some cases, and we'll see when we take particular moments of the cross-section, we can reduce this convolution to a simple product. But we can think of the convolution as acting as though it were a product. And we have a short distance part we can calculate times a long distance part, which we can't. Okay, this is in deep inelastic scattering. This is the parton distribution as a function of some variable C that we integrate over. And then this omega here is then the partonic cross-section, or if we're talking about form factors, it's the partonic form factors. What we can, in the factorized cross-section, we notice that the short distance part depends upon alpha s of some scale mu, and this is called the factorization scale. And the long distance part also depends upon that factorization scale, because you can always take a piece of the short distance part and say, okay, for these purposes, this is going to be part of our long distance part, because we can calculate it, so we can control that. And we'll see how that leads to evolution. And then we have the scales M. M is really lambda QCD in the language of quantum field theory. It's a scale in which the strong coupling becomes large, but more generally, it's just an intrinsic scale of the theory, which theory picks up. And it could also include the masses of light quarks. It could include, and in fact, the zero mass of the gluon is included implicitly in this F, but we're not going to calculate this in perturbation theory. We're going to take it to the lattice, for example, calculate it or measure it. Okay. All righty, so here we have M is then we describe as the infrared scale. Now, in some cases, M can be perturbative, and you can write this kind of cross-section in terms of perturbative quantities on both sides for certain cross-sections, in particular for something like jets at E plus E minus, where you can calculate that just entirely self-consistently in perturbation theory. As long as you don't make the scale M, say the mass of the jet, to be really at the hadronic scale. So in general, if you go out and you talk to people from the Large Hadron Collider, the short distance cross-section, calculable short distance, is where you look for new physics. That's where people discovered the top quark. That's where people discovered evidence, let's say, or discovered the Higgs particle. The omega long distance, the LD here, part is universal. So the new physics here is particular for the process you're looking at. The long distance part is universal for a given target or observed particle. Right? Observed particle to be a fragmentation function. So this, of course, this word universal is an interesting word. Nothing is totally universal. I mean, except what do they say? Taxes, death and taxes. But I mean, nothing, okay? So what universal means, you can use it more than once, okay? It appears in more than one. And then when it appears in more than one, you see what you have. If you know what the F is in some unknown left-hand physical cross-section, you say, oh, I'm going to go out and look at this, okay? If I can use the same FLDs, all I have to do is do a computation. That could take you like 10 years, but you could do it. So almost all collider applications have this, can be put in this form of a short distance part times a long distance part. The long distance part is universal. We have to get information about it outside of perturbation theory. The short distance part is something we can in principle calculate. And it enables us to compute energy transfer dependence in, for example, a semi complicated hadronic initial state for some outstate with this particular thing we trigger on, which is represented by Q. The short distance function is said to be infrared safe. That is, it depends only on the scales of the hard scattering. And if you, in your calculation, you encounter infrared divergences, you can be, if you've done it right, you'll always find a canceling infrared divergence from some other, one of the perturbative final states that you're summing over. So as we say, it requires a sum over a final state. So this is the general thing, short distance times long distance. And we recognize this as being exactly a generalization of that Feynman picture of deep inelastic scattering. Long distance is the distribution of partons in a hadron, and short distance in that case is the lowest order electron charged quark scattering. Okay, anything, I mean, one thing that's different here is that here the F is on the right of the omega. The other case it was on the left, but don't let that. Okay, we all kind of familiar with that, I guess. So now here's the thing that makes it really increases the generality. In particular, it increases this concept of universality. We have maybe an F that can be used in two different things. For example, it can be used in deep inelastic scattering for a parton distribution, but it could also be used in Drell-Yan, where we collide two hadrons and we look for lepton pairs coming from the annihilation of quarks and antiquarks. So there's two of them. But one thing about this is that it's not like you can do deep inelastic scattering at some one energy and be assured you can do Drell-Yan at the same energy. You really can't. I mean, and anyway, the kinematics is different. So how do we go from one to the other? So this is the other really, this consequence of factorization, which is if there is, whenever there is factorization, there is evolution. And to some extent, the reason why people have nerve to get up and talk about this stuff is because of what's on this transparency here. I mean, a slide, not transparency. I'm talking about looking in the past. So anyway, okay. We introduced a factorization scale, which we said, you know, the fact that you can factorize it has some content. And the content is that the short distance part only depends upon large momentum scales. The rest either doesn't contribute in the leading power or it cancels. So the physical cross-section, however, cannot depend upon the factorization scale, right? And you'll see this when you talk about renormalization in quantum field theory, you renormalize at some point, but the actual cross-section can't depend upon where I decide to renormalize. So therefore, we have this nice equation here. Mu dividing mu of the log sigma physical is equal to 0. But sigma physical is a convolution of two functions which both depend upon mu. Therefore, their mu dependence must cancel. If I change mu, I'm saying, oh, well, at 5 GeV, I'll put that in the hard part. No, wait a second, 4 GeV. So I'll change my factorization scale from 5 to 4, or from 5 to 6, or 4 to 6, or, well, you get the idea, right? All of those, in principle, should not change the physical cross-section at all. So therefore, we can use this familiar idea of separation of variables. It's what you do when you solve, you know, when you separate the angular variables from the radial variables in, you know, solving the Schrodinger equation for the hydrogen atom, for example. Okay, And so in separation of variables tells us that the mu dependence of the long distance function has to be the same, except for the sign, as the mu dependence of the short distance function. And that these derivatives can only depend upon the variables that are held in common between the short distance and the long distance. And the variables that are held in common are dependence upon mu through the coupling, alpha s of mu, and also if you have these will be in general the things like fractions x and so forth. But this is a schematic way of looking. Okay? And in fact, we'll find there are cases where there is, when we take moments of the cross section, this p will depend upon the moments that we chose. But so we have this physical, the independence of the physical cross section on the factorization scale, separation of variables, which tells us that the variation with the factorization scale of the long distance function is the negative of that of the short distance function. But remember, we can calculate the short distance function. Therefore, we can calculate its derivative. Therefore, we know the variation of the long distance function on the factorization scale. Wherever the factorization scale is large enough so that this alpha s of mu is meaningful. So we could have, we might want the fact, we might have this f here at, 100 GeV, and we'd like to know it at 2 GeV. We just have to solve this equation with the right-hand side being something we can calculate. As long as alpha s of mu stays reasonably small, we can do this as fixed orders perturbation theory. And the solution we find, we can solve for f and put that back in the cross section, and we can find expressions like this. Physical cross section at capital Q, value capital Q of the Hart scale is equal to physical cross section at little q. It's just the exponential of the integral from little q to big Q of some omega prime, p of alpha s of omega prime. And this is in schematic way, without the complications of what do we mean by our product and what was the convolution. This is all a perturbative QCD, one way or another. Okay. Okay, so to some extent, this is, I'm taking a lot of time dwelling on it because the rest is just applications of this basic set of ideas. Any questions about this? Yes.
So the factorization scale, you said at some point that we can choose it freely, but this doesn't work if we set the factorization scale to really low values, right?
Right. And we can see that right here, because when we try to set it too low, we lose the utility of this equation. The whole point is to get from this, something you calculate here, and use it with your long distance, to get information about your long distance functions. So you can transfer them from one scale to the other. Against scale, against scale, against scale, against scale, against scale, against scale. That's abuse starts to get too big. Of course, what's too big? And there are various, then we get into the art. And in particular, the determination of, this is really, really important issue when people want to determine, let's say, collinear parton distributions with hundreds, thousands of data points, all at different energies. And sometimes you have very, very precise data, very, very low momentum transfers, or relatively low, a few GeV. How should I balance the precision of that data against the unknown higher order corrections in alpha s of mu, and alpha s is getting a little bit bigger, maybe not so big, maybe it's 0.3, as opposed to the 0.1, but higher order corrections are difficult. If you don't know them, you don't know them. So you're hoping and you're trying to balance these different sorts of systematic uncertainties. The systematic uncertainties, and the uncertainties, both systematic and statistical in the data, and the unknown higher orders. Okay. But this simple equation shows that that's the door to trouble when mu gets too small, given that we have an asymptotically free theory. Any other question? Yes.
So what happens if we want to go to subleading order in the factorization?
I'm not quite
Like
sure.
if we want the next term in the factorization,
Yeah, we have to calculate it.
well, what happens with this story? Is
Nothing. I
Oh.
mean, it's the same story. In other words, this d omega, I mean, not nothing, but in fact, it's a lot more work. Okay. In other words, if omega depends upon mu through log of mu, you say, oh, d by d log mu of log mu is 1. That was easy, right? All I have to do to get this p from the calculation of omega at one loop, and it was an order of s, let's say, is to look at the log mu, the coefficient of log mu. That's it. And on the other hand, when we go to two loops, then life becomes more complicated. But the main complication is just calculating omega at higher orders.
Oh, I think I meant like if we wanted to go back to factorization and like m over q is not small enough that we
To higher
Yeah.
higher twist correction, power correction. Okay, this is the Wild West. So, I mean, you can, there have been a lot of work was put into that many years ago. Around 1990, there were a variety, kind of a flurry of advances in understanding how to incorporate consistently in evaluation in deep elastic scattering, in particular, non-leading twist. In hadron-hadron collisions, there's really much less work, although there's some work, in particular work I've been involved in and with J-psi production, the large PT, where higher twist can be important. And of course, there's a lot of work done at various in deep inelastic scattering because the JLab data is difficult to do without that. But what you would basically get is that there would then be the possibility to have, we have to generalize this set of equations here to include power suppressions in mu. And then, of course, it really becomes the issue of how low you dare to go in mu. Because what's dividing mu? Is it lambda QCD? Is it the mass of the pion? Is it the mass of the delta resonance? In which case, forget it. You got to really go to high energies. So this is best thought of in at very, very the asymptotically high energies, but it's pushed down more and more. And I think there's room for more insights into how to generalize this to non-leading powers. Alrighty. Okay. So here, I mean, a little bit more detail on this, on the next couple of slides. Collinear factorization. So here's the F2 structure function. You've seen the structure functions, of course, a whole bunch of them, and there'll be some overlap in the next few slides between, with, in fact, a lot with what you've seen from talks by Chicago Hatza. And so we have this, again, this was the O time. So this is a standard factorization. A quark arrives with momentum fraction C, and then C is larger than X. You can see the integral of C from X to 1. In this CA, it says, oh, then there's some perturbative radiation. And this perturbative radiation depends upon the ratio of X to C. It depends upon Q squared, and it depends on alpha S. So all our Q squared dependence is in here. And this is the thing called omega, short distance before. But typically in these structure functions, or they're labeled with a C. And here's the F, which is the parton distribution. So if in this case, this very simple case where there's only one parton distribution, in particular non-singlet, which is a linear combination of the quarks and cancels out the gluon. So it's like the difference between what you get with a proton and a neutron. It factorizes into a simple product under moments. So these Mellon moments, x to the n minus 1. This is a sort of standard moment since time immemorial. When I was, in your situation as a graduate. And then under these moments, with a very simple exercise to show that you get a product of the moments with respect to this variable, x over c, of the coefficient function and the moments of the collinear part-time distribution or singlet part-time distribution. Okay, so then we can separate variables in this expression in terms of n-dependent so-called anomalous dimensions. Okay, and what we find is this p tilde, really this should be the p d mu of this, is equal to some anomalous dimension. And this anomalous dimension here is gamma. That's like the old p that we had before. And so these moments of the structure functions can be written as just integrals again, where over the integration range, the coupling here varies with the integration variable. And again, here's the same issue of you go to too low of momentum, you try to make a mu naught too small, then your alpha s starts to do funny things as you get to the lower limit of integration, and you can't trust the fixed order result. So if you just, and this is a little bit of an exercise, if you put in one loop running coupling, just 1 over b naught log mu squared over lambda QCD squared, you get this explicit prediction for this structure function, the non-singlet structure function, in terms of its energy, how it changes with the momentum transfer. A ratio of logs raised to a calculable power. And famously, this gamma n involves a log of n, and hidden in that gamma n is all the secrets of threshold resummation, which is trying to understand what happens when you go to large values of n. You look at large values of n, you can see in terms of the moments of the structure function, that you're just integrating here with x to the n minus 1. When you do this with c, the larger n is, the more you're concentrated on what happens at large values of c in the part-time distribution. Non-singlet quark part-time distribution here. Okay, so this is kind of necessary. So as we've seen, okay, now a bit of comic relief. In effect, a beam of electrons is a machine for detecting quarks, and we talk about large X that I just referred to here. Well, these are typical, say so typical. They are the kind of extremely precise data that you can get from various experiments at moderate values of Q squared. Therefore, it gives us insight into where what's happening to the part-time distributions of checks. And anyway, it works quite well. This is still, actually, this is really quite old, but this really showed the power of these ideas, especially when you go to relatively small x. And of course, small x is to some extent the underlying theme of this school, but what's already from the Hera data, you can see that these exponentials of the gammas give large effects as you change Q squared, as x gets smaller. Here, x is 0.008, this lower curve, and then up here, it's 0.0013, about 8 or about 6 times smaller. And in that, these slopes are predicted by the theory. Again, it's the changes that the theory can tell you about. And we can see these slopes increasing as we go to smaller x, and we'll come back to that at the very end. Here, this is other values of x, larger values of x, and here versus Q squared, this F2, we can see flat behavior. And that's again also predicted by the theory. But the experiments, the original experiments that inspired the whole parton ideas, in fact, were experiments in this range. And what people were really surprised by is how flat these things are. And they called that scaling. And then they explained scaling by part-time model factorization. And then we go to incorporating the quantum field theory corrections. We get predictions that say, well, you were just lucky to see it flat there. It's going to really change when you go to small x and higher energies. And, well, that's what happened. Now, notice that as you go to smaller and smaller x, well, by the way, I mean, these are not normalized the same way. These normalizations were changed here to separate these curves. But as you go to smaller and smaller x, it's hard to get data at large q squared. You see, run out here at q squared just around 10. And the reason is because small x, just go back to the kinematics, small x requires large center of mass energy. And so there's kind of a limit. Any machine will have a minimum x where you're going to be able to get deep and elastic scattering with q squared greater than 1. It's more or less the invariant mass of the system is like q squared over x. So you better be prepared to come with q squared over x, s of the order q squared over x, if you want x to get really small. All right. So, and a similar analysis applies to all the structure functions. I mean, we just talked about the singlet here, and these are just, well, you've seen this before at Hata's talk. So spin require polarized distribution. So remember G1 and G2, you saw that, so I won't dwell on this. And these were kind of early predictions, and I think we saw the reference to this effort, which is ongoing by Florian Vogeltang and collaborators. So we do have some knowledge of these spin-dependent distributions, but a lot of work remains to be done, and that's, of course, what the EIC is all about. So all of the foregoing, okay, looks inward towards the hard scattering. The emphasis originally was on the verification of QCD at shortest distances and predictions of new physics signals at high energies. But the path to a fuller understanding of QCD, the theory, involves looking away from the hard scattering. Okay, there are two qualitative ways. We can go further back into the initial state before the collision and try to understand what's going on in the structure of nuclei and the language of parton. Or we can go farther forward into the final state after the collision to try to probe process of hadronization. So the questions we seek to answer will still be phrased in the language of hadronic structure and formation in terms of partonic degrees of freedom. And that's the philosophy that we saw in those bullet points that Alexei showed about the big reason for the EIC. We'd like to understand the origin of mass, and the way we're approaching it in all of these discussions is through the language of what we see as the fundamental degrees of freedom, the quarks and the gluons. Okay, all right. I mean, this is hopeless. All right, so okay, so here's some words. Let's see, I'll read them. To start, over short time scales, the quark doesn't have to be moving in exactly the same direction as the proton, just on average. And this little observation here leads to the idea of transverse momentum dependence, parton distributions, or TMDs. These cross sections factorize too into parton distributions and quote fragmentation functions for the outgoing hadrons that depend on the extra transverse motion of the quarks and gluons. Corrections here, however, are even more important than they are in collinear factorization. They're not just alpha S of mu, they have to do with the average transverse momentum divided by in connection with lambda QCD, but they can still be computed in principle. With electron scattering, we can measure the momentum fractions of the quarks, their transverse momentum variations, and how their spin is connected to the spin of the proton and their transverse momentum. Now, this is absolutely what you heard about yesterday morning. what I hope to just coming at it from the larger point of view, in the larger context will help. So what this does is it gives us a family of functions to measure, and together they demonstrate the full correlation of single quarks to the momentum and spin of the proton. And in fact, when you add together what we heard about, the energy momentum tensor, degrees of freedom in various matrix elements, and we'll come back to matrix elements, we really have the picture of the proton. So the quantum field theory expression for such distributions itself, it's a story, like the stories we talked about before. So here it is. So you recognize this is a TMD, all right? And this is one of these W's. It says W sub TMD. It could be the stable, it could be the direct line that we heard about yesterday. And so, like any of the stories, when you look at it in terms of correlation functions, it's read backwards to the way we read English. You start out with the initial state on the right. Some start with a proton. The photon scatters the quark here, and the quark is absorbed by this field, so it disappears from the proton. And there's a gauge length and a projection of spin, this gamma plus, and here the quark reappears. And then the proton is here. So this is kind of like the elemental story, right? You, at the beginning and end, you've conserved all of your quantum numbers, but you've done it in this very odd way. You just start with the proton, take a quark away, let the system evolve a little bit on the light cone or near the light cone for a TMD, and then put the quark back and say, voila, proton. And in this case, of course, it's a proton with the same momentum. And all this stuff here, the integral dx minus, d to ct, and the Fourier transform, it's just out to pick out the wave corresponding to the scattered quark. We say the scattered quark, we mean the one that in this matrix element disappeared and then reappeared with the same momentum. Okay, and so we can break this down in terms of spin dependent part, and beauty of spin is its dependence is just linear. And then we have this F1 and F1 transfers. So this is among the ways of writing this TMD. So, come back. So then another variation of this is electron-positron scattering to excited nucleons. So here, let's look a little bit more in the final state. TMDs are talking about the initial state. What is the proton really made of? How's it put together? Let's go a little bit further into the final state, and we can look in elastic or deep and elastic scattering, but not so deep, and not so elastic, but almost elastic. So here's the parton model picture, distribution times the lowest order quarks, quark electron scattering. So we're talking about the production of heavier, unstable versions of the proton. I guess I called it quasi-elastic. In this case, not just one of the quarks is scattered, but they're all scattered together. So what happens is that coming out, instead of a general object of X with a very, very high mass, and we sum over all X, we look for just finding one excited proton, a delta resonance or something like that. And then what we find is that the observed cross sections actually are very closely related to a, how should I say, an extrapolation of the perturbative structure functions. Okay, and so you see, here's the PQCD result for this low value of Q squared. Now, of course, to do this, it requires, again, an art, because we're getting into the very small scales. But still, Q squared, I mean, is like small, but just here, Q squared of 0.45 GeV. And yet, what happens is, and this was was moved forward, this kind of analysis at JLab, by people there. You see that the cross-section from these resonances, the production of resonances, almost saturates the extrapolation of the perturbative result. And here your Q squared of 3 GeV squared, it's reasonably hard. I mean, this is the scale that was seen in the original original experiments at SLAC. And as you go to larger Q squared, it's much, much less likely to get these resonances, and yet they fall very close to the perturbative picture. Yes, I'm sorry.
I was just gonna ask, so the solid lines are the PQCD prediction, and then the data point, like the wobbly.
Yeah, these are the actual data.
Okay.
So this goes by the name of quark hadron duality.
Uh-huh.
Quark picture supplies the solid line. Maybe extrapolated because it's going up way up to C of 0.8, things like that. But these are real data, and the two know about each other. So in some sense, what seems to be happening, the way I like to think about it, I don't know if it's useful or not, is that the QCD takes the cross section for single quark scattering as it goes to these almost exclusive limits. And to see these, you have to wait a long time because you have to see what the system decides to do with itself. It takes the probability for scattering a quark and it redistributes it. It says, well, I have a resonance here. What do I mean by resonance? It means it eats up the probability of the quark prediction and gives me a peak. So nearby, probability being that conserved thing that it is, which is called unitarity technically, it has to take probability away from neighboring regions. So in some sense, what we learn from this is that there is somewhere hidden in our understanding of QCD a picture in terms of redistribution of probabilities from the smooth partonic predictions to these peaked concentrations of probability when we form resonances at long distances. So anyway, but of course, these long distances aren't so long, right? Because these are, strong resonances.
Sorry,
Yeah.
I have one doubt. In the first plot, for example, all the points start from the same side evolution, but in the first plot, there are different initial points. So why
You mean,
this
you
difference
mean the data points?
in the first plot?
Uh,
You see that the points start, the curves
here?
start, yeah,
Yeah.
but the other plots start with the same
Well,
side value.
as you go at different Q squareds, these are kinematic, which you get from, I imagine. So in other words, as you, whoops, supposed to come back to this. As we Q squared increases, then to get to these low values of, to get to the masses of these resonances, they have to move to larger C values. Because the mass of the resonances as this variable C, which is like X, call it X. As X goes to 1, the mass of the final state is 1 minus X Q squared over X. Dividing by X doesn't make too much difference. It's really 1 minus X Q squared. As you go to a larger Q squared, then to get to the M squared, you have to go to a larger C. So in fact, it's probably a kind of nice exercise to really verify, with the right kinematics, taking into account the mass of the proton, that the first point marches to the right in these pictures as Q squared increases. So that's a really good observation that things are going on, that there's a lot going on. And it really took a lot of insight for people, which the first data of this kind of thing really goes all the way back to the observation at SLAC when scaling was first seen as a qualitative description of deep inelastic scattering. And people really pushed it. There's the names of Bloom and Gilman are associated with this kind of scaling, or sometimes called, instead of quark hadron duality, it's called Bloom-Gilman duality. Now, as far as I know, Bloom is not a quark and Gilman is not a hadron. But nevertheless, it has a certain pleasing sound. Okay, so anyway, let's see what else we have here in the kind of closing minutes. Okay, yeah, experiments about elastic scattering in the nucleon resonance. You can go to smallish q squared and look at elastic form factor. So when we're talking about elastic form factor of the proton, we're really going far into the final state. But then looking at the form factors associated with elastic scattering, we can measure things. Is there like thunder in the building? We're having a thunderstorm here. Anyway, so there are neat data about this kind of thing. This is a bit out of, there's certainly more data since these, you're able to find this. You can find exotic states and lots, JLab is looking for exotic states, things where somehow the lowest state is maybe two gluons or three gluons. Why not? And there are, in fact, from the lattice, we have led to believe there are hadronic states that are, in fact, primarily made out of glue, or they may be linear combinations of these so-called glue balls and quark pairs. And these are things which is a place where there's a dynamic interaction, I think, between the lattice and the experiment. So again, this is all in the theme of looking further into the final state. Yeah, DVCS. Well, we heard a lot about DVCS, so let me not dwell on it here because I can't, in fact, give as useful technical introduction. But this is kind of the picture here, and it's experiments like this, the DVCS and the corresponding one, where instead of a photon coming out, we have a meson. They reveal correlations between positions and momentum within the proton. So now, having spent a few slides in the final state, go back to the initial state to say, hey, what's going on? That we can find by thinking creatively about the kinds of final states we can look at. What you see here, here's our proton coming in, coming out with a slightly different momentum, big delta, where t is equal to delta squared, and then somehow or other, it's this picture of what's used to be called, maybe it still is, the handbag diagram. If you can see a handbag, I don't know, and there it is. Actually, I mean, this diagram, just historically, this was like a big deal because if you look at, remember our parton distribution, quark is taken out, quark is taken back. So people is put back. And so if we look at those kinds of distribution functions, they have this same structure here, but with a Wilson line. But in the olden days, when all these ideas were new, this really was, people thought of a parton distribution as being exactly this diagram at lowest order. We said, oh, this is what it is in the free theory. And so people said, there was an objection, and people said, yeah, but how can you ignore the interactions of this quark here? Okay, so now the way we look at it is this quark can be replaced by Wilson line, and there are interactions of the Wilson line with gluons, but those can be eliminated by I'm not going to take this, although if you knew who it is, you'd probably say I should. Okay. Right. Okay, so the point here about why we can do this is it's precisely because it was inclusive deep inelastic scattering. Now here we're going to come back and we'll ask that same question in DVCS in a slide or two. So this is kind of the end of these lectures as we explore the final state, now the initial state again. And okay, the factorization, analysis of and collinear distributions in TMDs depends on the localization of partons by hard scattering and the absence of final state interactions. That is the cancellation of all of the variations associated with different final states. Such factorizations are sensitive to local properties of hadrons and nuclei, not so much of their coherent structure. So for parton polarizations, not so much for orbital angular momenta. Well, okay, these, so it's great, but in other words, collinear and TMDs are great and for polarizations, but the orbital angular momenta required insights that we heard about last time. That's what this paragraph is telling us. And so what we came to and we saw, in fact, in yesterday's lecture, is to how we end up, instead of looking at a distribution in terms of a number operator for quarks, we get a slightly translated number operator where there's a skewness to it, where the proton comes in with one momentum and goes out with a slightly shifted momentum. And here I have the momentum, the outgoing momentum is being proportional to the incoming, but it's not quite that. So, yeah, so these are collinear fractions of quarks. I'm not quite sure why I put that there. So the generalized distributions, well, this should look familiar. So why don't I say, you saw all this, and Sterman was thinking about it too, just not as clearly. Okay. And of course, you saw all this, perhaps with a slightly different, this connection, again, the Wigner distribution is the kind of origin of all the others, integrate over various components of this 5-dimensional distribution. You can get everything in terms of all the things that we heard about yesterday. So what I'd like to do here is just say that here's one way of thinking about how it works. These closing moments. And I think I even said these words before. So here's DVCS, understood in the language that we've been discussing. So the first step is an electron exchanges. So here comes our electron and here's our proton. An electron comes in, right here, it's coming from the right and going to the left, and exchanges a photon of momentum Q with a quark that's inside the proton. So that's step one in DVCS. Step two, the quark travels some distance and then re-emits another photon. And step three, the photon escapes. Here it is. It's the happy photon. It got away while the getting was good. But the quark remains in the proton, which now has a different total momentum. It's just the difference between this big Q and this little q. Whoops. And yes. Yeah.
Sorry, I was gonna, just quick question. So for this photon interaction between the collision, I was curious on to whether or not the physics is similar to ultra peripheral collisions in heavy ions, because in that case, the claim is that the nuclei pass next, they don't, and they collide, but then there's like a photon and
it's kind of two of these. I mean, so in the ultra peripheral, here come two big charged things, you know, A equals 80 or something. And then each of these, or it's really the Z that counts. Z is 80. So there's a strong electromagnetic field. Photons arrive, one from one beam, one from the other, or one from one nucleus in the beam, or one from the other. And those two photons, each of them couples to some virtual loop of muons, of charm quarks, of you name top quarks, even if you go to high enough energy. And because they're supplying this energy to this virtual state here, there's now enough energy to bring those pairs to life. And so here, this is kind of a half,
okay.
from the electron point of view, it's always peripheral. Because it said, I sent out a photon, I was going to get it back, but you know, that's the way it goes sometimes. It's and I'll just live without it. Yes.
So from this picture, how do we differentiate deeply virtual Compton scattering from Compton scattering?
Oh, well, Compton scattering, a photon comes in, that's an on-shell photon. And a photon goes out. So it's on-shell in both cases. In some sense, I mean, the original diagram that describes the scattering of the quark here is the same.
Oh,
But by making this photon's very asymmetric in terms of their invariant mass, you can actually transfer just a little bit of momentum to the to the proton, and still, from a kinematic point of view, demand that this quark really doesn't go very far. So it doesn't, it's not trying, it wouldn't have time to escape. Well, if it did, you wouldn't get this event.
Yeah.
So this is the kind of picture. What I want to do is to derive this, or to emphasize this analogy, which we already heard, of these matrix elements to the matrix elements, which are the collinear parton distributions, or the DMDs. Okay, so people have measured things, we've seen about that, including gravitational form factor. I really thought, oops, let me go back here. And then we'll, yeah, well, okay, we don't have it here, but this is, again, this, you can, when you look now at the off-forward parton distribution, here you have a psi field, which absorbs the quark, starting with the incoming proton, and then you take that quark away. So far it's just like deep inelastic scattering, but then you give the quark back at a nearby momentum, but not exactly the same. And so this amplitude, which never was a cross-section, gives the same matrix element as the deep inelastic scattering cross-section, where you sum over all final states and hence reduce it essentially to a forward scattering cross-section. All right, let me, I'm going to wrap it up here and just mention to you what's in these other, at the very end here, the last 4 or 5. 2 more factorizations that are discussed on these slides. And one of them is transverse momentum factorization. So you get a more complicated looking factorization, not just in terms of momentum transfers, XA and XB, but also in terms of KTA and KTB. And you can look in Drell-Yan, or deep inelastic scattering. Here's the Drell-Yan form, where A and B produce a pair, a muon pair. The Fs are now TMDs. You have some short distance cross section. So you see this general form that we started out at the beginning. Calculable short distance, long distance to be determined. But now the long distance is in convolution with the short distance, not just in terms of the collinear fraction X, but also in terms of the transverse momentum distributions. And it's this factorization which is at the heart of some very famous results, which have to do with resummed results in terms of the transverse momentum dependence, and in terms also, you can, I mean, here in terms of transverse momentum, and also the you could also do it as in terms of the factorization scale. Okay, let me just leave it like that. So we get an exponential of some integrals here. There's a function A, which sometimes goes by the name of the cusp anomalous dimension. This is just copied out of one of Ted Rogers' slides. So let me just say, though, that what the takeaway is, if you have transverse momentum factorization, if that's true in a specific process, then you can write down the evolution equations. But now you have, instead of one equation, you have 2 equations. With those 2 equations, you can get the exponentials in terms of B space. Alrighty. And I'd just like to close by saying there's another factorization associated with very, very high energies, where, for example, if you have gluon scattering from a photon in the form of a dipole picture, say a pair of quarks, you can write down a factorized cross-section in this case. But here, at very, very high energies, the incredible insight is that the roles of the transverse momentum and the C, the momentum fraction of the gluon, are exchanged. And C becomes like a factorization scale, while KT becomes the active part of the convolution. So you choose a kind of factorization scale for C, and what you get is an equation here, which is for the C dependence of your distribution, which here is labeled psi. That. And the analysis of this equation and then what you get is, because you can calculate this short distance function here in terms of the convolution over KT and of C, you can derive an equation from this factorization. And this equation goes by the name, once it's put in the right form, of the BFKL equation, and tells you gives you an equation for the small x behavior of gluon distribution and related. And this is a bit of technical stuff. This is just to say what this equation looks like up at leading order. And here's the general formula you get, where you get this C to the minus omega, which is a really, can be a very, very large effect. So really, just like to point out that this kind of factorization is associated with the analysis that leads to the BK equation and the well-known, I'm sure we'll be talking about later, the Jim-Wilk equations, and the important role that's played by Wilson lines, which in some sense generate these, the distributions that factorize. So with that, I think it's about 5 minutes after. This is the same as I said last year. Yeah, the EIC should be exciting, and enjoy the school and the adventures beyond. So thanks for your attention.
Thank you. No comments?
Well,
Thank you, that was very good. I really appreciate it.
well, thank you. You've been a great group. I feel like a comedian. It's like, oh, you've been a great group. Good night. You know?
What happens, I noticed this school in particular, when I ask them to ask questions, they are so intimidated by. Nobody asks questions. As soon as we say now there's coffee, they will start queuing.
Okay, that's great. So let's have some
Peter.
coffee.
Go ahead.
Oh, yes.
So previously asked about the lower limit of the renormalization scale, right? So what about the upper limit? Or is there none?
Well, that's the part where and that gets interesting. The upper limit, you have to tailor to the observable, the particular cross section that we're talking about. Otherwise, if we could choose the upper limit to be as large as we wanted, what we could use arbitrarily small coupling in an asymptotically free theory. Well, what we would find if we choose it too large is that we would start to get logs of the hard scale divided by the renormalization, factorization scale. And if we make the factorization scale artificially large, our alpha gets smaller, but it will be exactly compensated by increasing explicit logs of the hard scale divided by the factorization scale. So this is the case. This is why in deep and elastic scattering, if your data goes up to 10 GeV squared, you're not going to benefit from the fact that alpha S of the Z mass is 0.1. You'll have to live with an alpha S of 0.2 or so at your 10 GeV squared. So it's that, again, it's always, the point is the reason we can calculate these things is because when we do the lowest order factorized form, or next to leading order typically being just the tree levels, doesn't have any dependence on factorization scale. The factorization scale appears as log of mu squared over q squared, exactly times well, in the original convoluted form times the splitting function. We saw the splitting functions. There I didn't really write them. I didn't write them down. I hope they're familiar with the kind of Alterelli-Parisi splitting functions, Or in the cases where you have more sophisticated transverse momentum dependence, you get other kernels.
Can you give an example where a factorization fails for a certain process?
Factorization fails for every process where you say, I want this specific, this factorization. You see, that's the problem. I mean, why are people always trying to make factorization fail? But to some extent, that's exactly what we should be doing. When you start to look at, so if we start to do, well, we could start with the inclusive cross-section, deep inelastic scattering, inclusive cross-section, and then we could say, oh, well, what I'll do is I won't sum over every final state. I'll just sum over final states that have a jet that's a current jet, so-called. It's a jet in the direction of the scattered quark. And then I could say, well, what do I mean by jet? Well, maybe I'll choose a cone thing and I'll say the jet's inside kind of a big cone. And then if I define that properly, I can get a perturbative cross-section for that with a hard scattering function that's factorized exactly like that. Then I say, okay, I'm going to make that cone smaller and smaller. And as I do so, what I'm going to find is I'm going to have logs of the size of that cone. And then eventually I start to see that I get logs of the size of that cone times the momentum transfer, Q, divided by the factorization scale. And then I say, oh, but I'm a clever sort of person. I'll realize that actually there's another factorization I could do where I factorize the jet dynamics from the rest. And I use maybe an effective theory to do that, or I just do it by hand. And so then I can get another equation, consistency equation, mu prime d by d mu prime on that thing where mu prime is the scale of delta times Q, something like that. And so that could work. And I could make delta pretty small and resum all the logs of delta. But eventually I'll end up with an integral over some mu prime, d mu prime over mu prime with an alpha s of mu prime. And with my delta, its lower limit will be set by delta. When it gets too low, my coupling would become large. And if I'm lucky, I can then use renormal-on arguments to say what it will imply the necessity of power corrections. Because the perturbative theory itself will induce power corrections. You say, well, how could that happen? The way it happens is because the theory knows about lambda QCD. Despite itself, it knows about lambda QCD. And when your scales start getting competitive with that, perturbation theory fails. And in a good case, you can control that failure, or at least see the minimal kinds of non-perturbative corrections that you'll need. Those would be power corrections. So this is a case where what happens is the original factorization doesn't really work. You do a modified factorization, but hard as you try, if you keep making your final state more and more exclusive, which means more and more sensitive to the long-time behavior of the theory, making that sphere that we talked about to define conceptually the running coupling, making that sphere larger and larger, the theory will object at some point, and you'll have to add power corrections that you can't get from perturbation theory alone. So in fact, it's that controlled, organized forcing of factorization breaking, which may, I like to think will as the future goes along, lead us to a better understanding as we explore these regions away from a hard scattering, trying to go further back into the past and further into the future. But it'll all be organized about how we define what we see in the final state. We say, okay, I'll settle for everything. No, let me be a little more picky, but let me do it in an organized way. Then I can maybe learn something about how that system is evolving. Any other questions? For no questions, you did pretty good. All right.
Excellent. Let us thank George.
Just a couple announcements. This evening we have a free night, so you get a little bit of break. But that also means we don't have discussion. So I encourage you, if you have other questions, you can catch George over the coffee break. And instead, for those who would like, it's optional, but for those who would like, we were going to head over to Port Jeff. And now that your meal cards work, you might enjoy some good seafood. The steam room has relatively reasonable seafood, but there are other places over there. Could I see who brought a car and might be able to drive people tonight? What cars do we have?
So I have one, but I can take people, but I have office hours from 5 to 7, so.
Okay, all right. So the train actually goes there, not every 90 minutes, but yeah, so people if people want to go one way and then
Yeah.
take the train back, you have a car here and you have a car there. And I have a couple places and the train also goes. So I'll get you guys over the break. We'll try to figure out, I think we'll have enough for everybody to get over there one way or another. Okay, anything else or?
Coffee is there. I sent you an example of it.
No, I don't think so. I mean, it depends. We'll see. Sometimes people don't show up to the office hours at all. Also, I went to get breakfast
Okay, yeah.
and I.
How to do these extremely elementary.
So literally, as I put
Yeah,
coffee on the car, like,
I should.
so it took me like 10 minutes to clean it up.
Yep.
But extra layer.
Parking, it's off.
So,
So, yeah, I'll try to.
yeah, he said.
Yeah,
like,
just be careful that there's
So
right in front of the steam room, if you go to the steam room, it's free parking. But
I was so-
otherwise, there's no parking.
Nice to meet you.
Oh,
I work with Helen,
So-
Kane.
so just-
we do,
Watch for that.
I
And
do strangeness,
I'll
but
send
they
you
do
guys a
yes.
map.
Star and
you do.
in,
my last
I do strangeness, but our group usually does jets.
Do you want to just